Hello. So today we'll move to linear algebra. We'll do the first steps in linear algebra. So first of all, let's discuss about Gauss-Jordan elimination. You really need to take a look at the reading materials I just sent you, right? So this is just examples of building on the reading materials. Right? So here is an example. Solve the system. So let's see, x1 plus 2x2 plus x3 minus x4 plus 2x5 equals to 1. 2x1 plus 5x2 plus 2x3 plus x4 plus 4x5 equals to 2. And then 4x1 plus 9x2 plus 4x3 then minus x4 plus 8x5 equals to 4. So there's a system of linear equations, non-homogeneous because we have not only zeros on the right-hand side. So how to solve it? We operate with augmented matrix. Augmented matrix is the matrix of the coefficients and the free coefficients. So let's see, 1, 2, 1, minus 1, 2, and then 1. Normally, there's the augmented matrix. We should put a tiny separation line here, but we will not do it. Right? We understand the last column. If we speak about the augmented matrix, that's why the last column is the column of the free coefficients. So 1 will be a 2 and will be a 4. Second line, 2, 5, 2, 1, 4, and after the line is 2. And third line is 4, 9, 4, 9, 4, minus 1, 8, and then a 4. Now, let's start the Gaussian elimination process. So pick up the pivot is upper left corner, and then create zeros below. And then after you do this, go the next pivot. You go travel southeast, right? And then create zeros below. So always create zeros below and move from left to right. And then second step, create zeros above and move from right to left. So it's like this. Zeros below, move from left to right. Zeros above, move from right to left. Okay, so let's see. Create zeros below. Multiply the first row by minus 2. There's a symbol. I want to multiply the first row by minus 2, add the second row. Then I multiply the first row by minus 4, add the third row. So what do we get? First row remains the same. So 1, 2, 1. Minus 1, 2, 1. Second row, 0, 1, 0, 3, 0, 0. Third row, 0, 1, 0. Four minus 1 is 3. Then minus 8 plus 8 is 0. Then minus 4 plus 4 is 0. So row number 2 is, intrinsically row number 2 equals row number 3. But now, let's go down here, and this will be the next pivot at this moment. So we create the zeros below, and then we create zeros below and move from left to right. So this will be our next pivot. Create zeros below. So multiply the second row by minus 1, add the third row. Okay, so since the augmented matrix conveys all the information in the system. We really don't need the system, so that's the original problem. So let's gain more space by erasing the system, because the system can be recovered from this augmented matrix anyway. Okay. Now, multiply the second row by -1, add the third row. So what will you get? Let me resurface here. First and second rows remain the same. So 1, 2, 1, -1, 2, 1. 0, 1, 0, 3, 0, 0. Then 0, 0, 0, 0, 0, 0. As a general feature of the Gauss-Jordan elimination, the 0 rows are always heavy. They're filtered at the bottom, right? The 0 rows. So we created zeros below, right? And move from left to right. Now, second step, create zeros above and move from right to left. So what's next? This will be the pivot, and I want to create a 0 above. So multiply the second row by -2 and add the first row. So what do we get? In doing this, multiply the second row by -2, add the first row. Row number 3 and row number 2 are the same. So just write them again. So 1, 0, 0, 6, 0, 0, 0, 0, 0, 0, 0. Row 2, 0, 1, 0. 3, 0, 0. Row number 1. So multiply the row number 2 by -2, add the row number 1. So 1, 0, 1. -2 times 3 is -6. With the -1 is -7. -7. Then we get a 2. Then we get a 1. So this method is called a reduced row echelon form. So it's row echelon because the structure is like this. 0 rows are at the bottom, which it is, 0 rows at the bottom. Then we have a staircase of ones in the column of a leading. These are the leading ones. So the leading ones. In the column of a leading one, there is only zeros except that particular leading one. Okay, once we are done here, okay, we don't need anything back. Let's continue. Once we got here, we brought the matrix to a reduced row echelon form. So let me find an application. Reduce row echelon form. Reduce row echelon form is the matrix. At this moment, we have to be clear what are the leading unknowns and secondary unknowns. So leading unknowns are x1 and x2. They correspond to leading ones. Don't forget there is a tiny dotted line here separating the coefficient matrix from the free coefficients. So leading unknowns are x1 and x2. Secondary unknowns are the unknowns which are not leading. Secondary unknowns are the unknowns which are not leading. So x3, x4, x5. At this moment, secondary unknowns become parameters. That's the idea of the sorting the system, become parameters. So what we got here? Let's put x1 equals to x2 equals to x3 equals to x4 equals to x5 equals to. Okay, so secondary unknowns become parameters. X3, X4, X5 are parameters. So let's invent some names for the parameters. Let me put in an S, P, and a U. They are parameters. Let's call them S for X3, T for x4 and U for x5. Now, we understand this is exactly the system. So we understand like a code for the system. It's an equal here, separating equations from equal for the right hand side, from the three coefficients. How do you read the first equation? X1 plus 0x2 plus x3 minus 7x4 plus 2x5 equals to 1. How do you read the second equation? 0x1 plus 1x2 plus 0x3 plus 3x4 plus 0x5 equals to 0. So every equation is code for an equation, right? So now once we got the secondary unknowns as parameters, we solve for the leading unknowns. So x1 equals to what? So this is x3, x4, x5. But this is S, P, and U. So we got x3 is S, x4 is T, x5 is U, x1 will be, let's imagine we move everything on the right. So it's move S from the left to right becomes -1. -7 from left to right becomes 7. 2 from left to right becomes -2. So what will be x1 is minus S plus 7T, because move from left to right, minus 2U, and 1 is already on the right, so don't have to move anywhere, so plus 1. So because we move those variables from left to right, 1 becomes -1 if you move to right. So S becomes minus S if you move to the right. So minus S plus 7T minus 2U plus 1. What about x2? Move to the right is minus 3T. And that's it. So this is the solution of the system in parametric form. Solution in parametric form. We are more interested in a solution of the system in vector form. So you want to make vectors out of the variables x1 through x5. So how to make a vector out of them, organize them as a column vector. So for the vector form x1, x2, x3, x4, x5, a vector in the solution space of the system equals to, let's organize this. We need S's, T's, and U's. So let's try to organize like S times a vector to be determined, plus T times a vector to be determined, plus U times a vector to be determined. And then we have other things other than S, T's, and U's. We have constants. So plus a constant vector. That's how we evolve towards find a vector for the solution. That's the way of organizing the information, right? Now read those equations and put them there. So what is x1? Minus S plus 7T minus 2U. So S goes with -1, minus S, plus 7T, put a 7 under T, minus 2U, put a -2 here, so to get a -2U. And then the constant number is +1, so 1 here. What about x2? X2 is -3T, so you have to put a -3 on the second line for the 3. Otherwise, there is no S, there is no U, there is no pure number. So 0 here, 0 here, 0 here. Next, x3 is S. So just to convey the information, x3 equals to S, put 1 under S because x3 is S and nothing else. So 0, 0, 0. x4 equals to T. So put under x4, get 1 under T, and then nothing else. And finally, x5 equals to U. We'll put a 1 under U, and then nothing else, 0, 0, and 0. And that's the solution of the system in vector form, right? Which we'll use quite a lot in the next steps of linear algebra. Solution in vector form. So okay, so that's basically how to quickly solve linear systems. So if a system has a solution, the system is called consistent. There are also systems that have no solutions. Let me give an example, quick example. Inconsistent systems, just in case you meet one system inconsistent, don't be afraid. There are also inconsistent systems. That means no solutions. So the system is, let's say, x1 plus x2 plus 2x3 equals to 2, 2x1 plus 2x2 plus 4x3 equals to 1. Look at this system. Let's try to solve the usual system, to use our usual method to solve this system. Augmented matrix. Start with 1, 1, 2, 2. Then 2, 2, 4, and then we get the 1. What's the pivot? To start, it is the pivot, 3 zeros below, so minus 2 here. So what do we get? First row remains the same, 1, 1, 2, 2. Second row, 0, 0, 0. So multiply the first row by minus 2, in the third row. So we get a minus 3. But if at any moment we get only zeros under for the coefficients of the variables, and on the right the free coefficient is not 0, how do we read this equation? What would be in our mind? That's our mind. How to read this? 0x1 plus 0x2 plus 0x3 equals to minus 3. So 0 equals to minus 3, which is a contradiction. So that's the signal of the fact the system is inconsistent. System is inconsistent. Okay, so inconsistent system is no solutions. Consistent system means it has solutions, right? Okay. So now let's try to move on with discuss a little bit about matrices and operations in matrices. Again, paramount is reading the just go over the reading assignments I sent you. So otherwise, so here is just a clarification, but the reading assignment is important. So matrices. Let's discuss some operations. Matrix addition is right. So 7, 1, 3, 11 plus the matrix. We can only add matrices which are the same type. So same number of rows, same number of columns. So plus minus 3, 1, minus 4, 4. How to add? Add elements which are exact in similar positions. So what we get here? Upper left corner, upper left corner. We add upper left plus upper left. So 7 plus minus 3 is 4. Upper right plus upper right, we get a 2. Lower left plus lower left. So we have lower left plus lower left, right? Add them together. 3 plus minus 4 is minus 1. And then lower right plus lower right. 11 plus 4 is 15. How to add matrices? This is how to add matrices. So matrix addition. Then matrix multiplication by scalars. So let's see, 7, 1, 3, 11. Multiply this matrix by 4, right? Multiplying a matrix by a scalar is multiply every entry of the matrix by the scalar. So we get 28, 4, 12, and 14. Multiply every element, every entry of the matrix by 4. Right? This is how we multiply. What about if we multiply a matrix by 0? Then we have only 0 entries. 0 times 7, 1, 3, 11 is the matrix. The null is called the null matrix. That's the easy part. So non-easy is the matrix multiplication. Let's discuss matrix multiplication. Okay, so let's pick two matrices. For simplicity, let's make 2 by 2. Otherwise, same thing, only the bigger amount of data. So let's see matrix 4, 3, 1, minus 1, multiplied by the matrix. So we can only multiply an m by n matrix multiplied with an n by p matrix. So if you multiply an m by n with an n by p, make sure that these two disappear. The result of multiplication of an m by n with an n by p, so that those numbers which are interfere with each other in the middle must be the same. We get an M by E. So imagine two particles, antiparticle, antiparticle annihilating each other. So they disappear. So you get M by P, that's what's left, M by P. So a 2 by 2 matrix multiply with a 2 by 2 matrix. They're okay here. So we get a 2 by 2. So if you multiply, in general, if you multiply a square matrix with a square matrix of the same size, we get a square matrix of the same size. So it's straightforward to multiply a 2 by 2 with a 2 by 2, and the result will be a 2 by 2. So let's find an example. The matrix is 4, 3, 1, minus 1, multiply with 1, 1, 0, 1. How to multiply two matrices? Row by column. So let's see. What will be the element here? So this element, row 1, column 1. Row 1, column 1. So how to get element in the matrix product in row 1, column 1? Well, simply multiply in the sense of a dot product, row 1, column 1. So we are talking about a dot product. The vector 4, 3 dot product to the vector 1, 0. So first plus second, second. 4 times 1 plus 3 times 0 is 4. So row 1, column 1. What about row 1, column 2? Row 1, column 2. So row 1 here, column 2. So 4 times 1 plus 3 times 1 is 7. What's here? Row 2, column 1. So what do we get here? Row 2, let me put a different color. Okay, so we put here row 2, column 1. Row 2, column 1. So what do we get here? First plus second, second. First is 1 times 1 plus minus 1 times 0, we get a 1. And finally, in the lower right, we get a row 2, column 2. Okay, row 2, column 2. So 1, 1, dot product, it's a dot product of vectors. Multiply in the same dot product. First plus second, second. So 1 times 1 plus minus 1 times 1 is 1 minus 1, which would be a 0. So that's the result of the matrix product of those two matrices. What about if we multiply in the reverse order? So keep very well in mind, in general, the matrix product is not commutative. So AB is not necessarily the same with BA, even if both of them are defined on the same size. So let's see, what about, take the same matrices because we got here 1, 1, 0, 1, multiplied by the same matrix on the right, 4, 3, 1, minus 1. So the same matrices, but multiply in the opposite order. Okay, so let's see. First, 4 plus 1 is 5 here. 1 second, 3 minus 1 is 2. Second first is 1. Second is minus 1. So this should be, let's call this matrix A, let's call this matrix B, and this will be the matrix AB. So what about if we multiply them in the reverse order? This will be the matrix B, and this will be the matrix A, and this will be BA. So as a result of our work, AB will be, AB is 4, 7, 1, 0, and BA is 5, 2, 1, minus 1. Right. So in general, AB is not necessarily equal to BA. Yet, it's interesting, very interesting fact. Always, if we have a square matrices multiply AB and BA, we get a square matrix of the same size. If A and B are both square, both n by n matrices, we can multiply then AB and BA, like we did here for 2 by 2 with a 2 by 2. In both cases, they are not equal, but the sum of the main diagonal elements is the same. So basically, the sum of these two elements, we use a color show here. The sum of these two elements equals the sum of these two elements. And one of the exercises I will assign a little bit later is to prove this, that always the sum of the elements of the main diagonal elements of AB is the same with the sum of the main diagonal elements of BA if both AB and BA are square matrices of the same size. Okay, so let's discuss more matrix products. Let's do 3 by 3 matrices. I'll give you some interesting examples. Say, for example, A equals to a 3 by 3 matrix 0, 1, 0, 0, 0, 1, 0, 0, 0. It will be an interesting phenomenon. What happens in this case? Let's calculate the powers of A. So calculate A squared, A cubed, etc. So let's see what do we get. So A squared will be the matrix multiplied by itself. So 0, 1, 0, 0, 0, 1, 0, 0, 0, multiplied by itself 0, 1, 0, 0, 0, 1, 0, 0, 0. It will be a matrix 3 by 3 with a 3 by 3 is a 3 by 3. So let's discuss first. 0 times 0, first, second, third. We get a 0. Second, first, second. 0 times 1 plus 1 times 0 plus 0 times 0, still 0. First, third. 0 times 0 plus 1 times 1 plus 0 times 0, we get a 1. Then, second, first. 0 times 0, 0 times 0, 1 times 0, all zeros. Second, 0 times 1, 0 times 0, 0 times 1 times 0, all zeros. Second, third, 0 times 0, 0 times 1, 1 times 0, all zeros. Third, first, but because the third row is only 0, 0, 0 multiplied with whatever you want is still 0. So 0, 0, 0. So basically what we get here, the area of the ones diminished for A squared. Now, interestingly, what will be A cubed? A cubed is A squared times A, and this is how you do normally subsequent powers. So A cubed is A squared times A. We already got A squared be 0, 0, 1, 0, 0, 0, 0, 0, 0, multiplied by this A squared. A will be 0, 1, 0, 0, 0, 1, 0, 0, 0. Again, a 3 by 3, the 3 by 3 is a 3 by 3. First, it's 0, of course. First, second, again 0. First, third, 0. Second row and third are both 0, so no matter what we multiply with, we get zeros. So interestingly, A cubed is a null matrix. Another property, when you know the null matrix, put it in some form that like a fancy zero, so to make sure that it is not, we are not talking about a zero, the number, we are talking about a zero, the matrix. So if you really want more explicit, 0 sub 3 by 3. The null matrix 3 by 3. So A cubed is a null matrix 3 by 3. So for matrices, we can have a non-zero matrix, which we raise to some power, get a null matrix. This doesn't happen for the normal numbers. If a number is non-zero, then the powers are also non-zero. Some important matrices, when we multiply, a very important matrix with n by n is identity matrix, very important. What is it good for? Identity matrix, I sub n, is an n by n matrix which is ones all the way on the main diagonal, and then otherwise we have zeros. That's I sub n, identity matrix n by n. For example, I sub 2 is 1, 0, 0, 1. 1 is on the main diagonal and 0 in the rest. That's the idea of identity matrix. What's important about identity matrix? Identity matrix multiplied with any other matrix of the same size is the same. So it's like what is 1 for numbers is identity matrix for matrices. So I sub n times A equals to A times I sub n equals to A for every n by matrix A. That's why I sub n is called identity element under matrix multiplication. So I sub n times A equals to A times I sub n equals to A for every n by n matrix A. Let me illustrate this by using the case of 2 by 2 matrices. Multiply 1, 0, 0, 1 identity matrix I sub 2, multiply by a 2 by 2 matrix A, B, C, D. What do we get here? First, we get A. Second, we get B. First, we get C. Second, we get D. We got the same matrix. So identity matrix 1, 0, 0, 1 multiplied by ABCD is ABCD. And the same is happens if we identity matrix we put it on the right. So A, B, C, D multiplied with 1, 0, 0, 1. First, we get A. Second, we get B. First, we get C. And second, we get D. So identity matrix I sub 2 times A equals to A, and A times I sub 2 equals to A. Okay, so one more thing before next week. Let's discuss a little bit about inverse matrices. So for the moment being, for just to start with, we'll do more next week. Let's discuss, and I'll give you more in the homework. Once you read the reading material about matrices, homework also will involve inverses of matrices of higher order. So for the moment being, what is an inverse matrix? So A is an n by matrix. It's called invertible. If there exists an n by matrix B, such that AB equals to B times A equals to identity matrix n by n. It's like for numbers. For example, as a real number, 2 is invertible because there is another real number which is 0.5 with the property 2 times 0.5 equals to 0.5 times 2 equals to 1. One is for real number, what identity matrix for matrices. So a matrix is invertible if there exists another matrix B, which turns out to be unique with the property AB equals to BA equals to I sub n. If such a B exists, B is unique, and B is unique and denoted by A inverse. So in other words, the inverse satisfies A times A inverse equal to A inverse times A equals to I sub n. A particularly simple case is the case of 2 by 2 matrices. So that's what we discussed today. Case of 2 by 2 matrices, which is the simplest one. So for example, the matrix A is A, B, C, D. What does it mean invertible? To check that this invertible is equivalent, this equivalent is determinant of A is not 0. That of A is sometimes denoted by like an absolute value, but be aware that we use absolute value for matrices just a determinant. Determinant of A, or also denoted by modulus of A, is which is AD for a 2 by 2 matrix. It's not for all matrices. For 2 by 2 matrices, the determinant is a product on the main diagonal. So A times D goes with plus, and B times C goes with minus. The determinant of A is AD minus BC. AD minus BC must be non-zero. So there's a condition for a 2 by 2 matrix A, B, C, D to be invertible. The determinant is A, D. Product of the main diagonal minus the product of the secondary diagonal is non-zero. In which case, A inverse equals to 1 over AD minus BC, which is like a scalar taken in front of a matrix. You know how to multiply now matrix with scalars. 1 over AD minus BC times the matrix in which the main diagonal elements get flipped. Instead of AD, we get DA. Secondary diagonal elements with B and C, they don't get flipped, but they acquire a minus sign. Instead of BC, we get a minus B minus C. Okay, so let's, there's the formula for the inverse of a 2 by 2 matrix, provided AD minus BC equals 0. Otherwise, if AD minus BC is 0, the matrix is not invertible. Let me give you an example. I only leave the ones here. Here's an example. Let's say A equals to 1, 2, 3, 4. And just for the fun of it, 1, 2, 3, 4. So let's find out whether A is invertible. If it is invertible, find the inverse. Okay, so is A invertible? Here's the question. If so, find A inverse. Solution. We got here how was the way to check that the matrix is invertible? AD minus BC equals 0. So determinant of A equals to product on main diagonal minus the product of secondary diagonal. So 1 times 4 minus 2 times 3 is 4 minus 6 is minus 2, which is not 0. Therefore, A is invertible. So we now know that A is invertible. Now, what is the inverse? So once we check this, that we did, now we know that A is invertible. Use this formula for the inverse matrix. Then A inverse will be 1 over determinant. You already got determinant is minus 2. 1 over minus 2 times the matrix in which the main elements are flipped. Instead of 1, 4, get a 4, 1 here. The secondary diagonal elements acquire a minus 1. So instead of 2, 3, you get a minus 2 here, minus 3. So basically, we have to multiply this matrix by the scalar minus 1/2. So let's do it. Multiply by the scalar minus 1/2 amounts to multiplying each entry of the matrix by minus 1/2. So what do we get? 4 times minus 1/2 is minus 2. Minus 2 times minus 1/2 is 1. Minus 1/2 times minus 3 is 3/2. And 1 times minus 1/2 is minus 1. There's the inverse matrix. So let's check our work. So what will be A times A inverse? A was 1, 2, 3, 4. A inverse, according to our algorithm, is minus 2, 1, 3/2, and minus 1/2. Equals. What do we get here? First. Minus 2, 3/2 times 2 is 3. So 3 minus 2 is 1. Second. 1 minus 1 is 0. Second first. Minus 6 plus 4 times 3/2 is 6 is 0. Minus 6 plus 6 is 0. And finally, second. We get 3 minus 2, 4 minus 1. 4 times minus 1/2 is minus 2. So we get 3 minus 2 is 1. So excellent. So we just proved that A times A inverse is, that'll be enough to prove that A inverse exactly is the inverse of A. So we just check that the matrix we got here, this one, indeed functions as an inverse of the matrix A. Okay, so have a great weekend and don't forget about read the reading materials and solve the homeworks. Okay. So have a good weekend, and I'll see you next week.